our esteemed faculty, and one and all present here. We are honored to have you, sir, in our FDP program 2023. In recognition of your presence and remarkable achievements, I would like to invite our Sir Rajiv sir to present sir with a token of appreciation. Thank you, sir. Dr. Satyam Agarwal is an assistant professor in the Department of Electrical Engineering at IIT Ropar, India. He obtained his PhD in Electrical Engineering from IIT Delhi in 2016, and prior to that, he completed his MTech degree in Signal Processing and Communications from IIT Kanpur in 2012. Before joining IIT Ropar, he served as an assistant professor in the Department of Electrical and Electronics Engineering at IIT Guwahati. Additionally, in 2017, he worked as a postdoctoral researcher at Politecnico di Torino in Turin, Italy. Dr. Agarwal's research focuses on wireless communication networks, particularly next-generation networks, B5G, 6G networks and architecture, and airborne UAV networks. He has been recognized for his work and received the DST Inspire Faculty Award. He has also secured several research grants from organizations such as DST Serve, ISRO, the Ministry of Earth Sciences, the Punjab Skill Development Mission. Dr. Agarwal has contributed extensively to his field, having published over 30 research articles. He is an esteemed senior member of the IEEE. I would like to invite you, sir, to go ahead with today's session on harnessing machine learning in 6G networks.
Thank you so much for the kind introduction, and I would like to thank the organizers for inviting me to this FDP. Let me start. Let me first understand what the audience is all about. So, how many of you are students? Okay, and the rest I guess are faculties. Okay. And in students, how many of you are PhD students? Okay. All are bachelors or masters? Bachelors. Okay. So what I am going to talk about is machine learning in communication networks. Okay. So you know that machine learning. I mean, everyone of us nowadays now works on machine learning, AI, ML, everywhere you use that, and you're going to see the improvement in the system. What I'm going to do is that I'm first going to motivate you on why we would require machine learning in the next generation networks, that is the 6G. So 5G has been already deployed, and we are seeing certain improvements in 5G standards now, and then we are proceeding towards 6G standards. So we expect that by 2030, 6G is going to be deployed. So in 6G, we will first understand why we require certain systems which are more efficient. Okay, and to come to that level, come to that performance levels, we will require machine learning to realize those networks. Okay. So this work, so what I'll do is that the first half of my presentation will be devoted to 6G and its requirements, and in the second half I'll talk about what we are doing in realizing these 6G systems. So the research work that we are doing, so this is jointly with my PhD student Aram at IIT Ropar. So let's just start with what the 6G is all about. Okay. So we know the evolution of communication systems. So we started with 1G, 2G, 3G, 4G, 5G, and then the future is 6G. Okay. And each of these different generations, the emphasis was different. Okay. For example, 1G was mostly about talking. Okay, you wanted to talk to the other person, and it was based on analog communication systems. Then came the 2G, which was, so from 2G we had the digital communications, and the 2G prime focus was voice as well as a small SMS, okay, small messages they would like to transmit. Then the third one was the 3G, which was based on CDMA, which was catering to certain small multimedia applications. Then came the 4G. Now, I think most of us are now lying in this regime of 4G, where we could be connected to the internet almost all the time. And then the 5G came up. It's now deployed in India. Okay, India, I would say, the world leader in the deployment of 5G networks. And this majorly catered to high-speed internet. And then what is going to be 6G? Are we going to see even more high-speed internets? Or what is so fascinating about 5G, about 6G that we are going to see? So what we are going to see in 6G is, of course, ultra high speeds. We want to see large uplink, downlink speeds. Then ultra low latency, the latencies between the end-to-end transmissions, you want to reduce them. Then massive connectivity, you want to connect majority of the devices on the internet. And enhanced reliability, you want to have your communication systems to be more reliable. Okay, I'll talk about all these things in the future slides. So I'm not discussing in detail now here. So there is something called as the International Mobile Telecommunications. This actually is the part of the ITU. ITU is the International Telecommunication Union. Okay. Now, how these standards are made, I think you should be familiar with how these standards come about. Okay, when we talk about 4G, 5G, 6G, or we talk about Wi-Fi, we talk about Bluetooth, anything you see, any wireless application you see, there is a standard to it. Okay. So we should understand why these standards are essential. Now suppose if I come up in India, let's say from IIT Ropar, I come up saying, okay, this is my standard. I want to build devices according to this set of standards. Set of standards means set of rules. How you want to communicate. For example, what is the bandwidth, what is the modulation scheme, what are the code rates, and so on. Okay, so these are a set of rules over which you communicate. Now, if I decide my own set of rules and you decide your own set of rules, so there will be two different devices which will not be able to communicate with each other. Okay, so you want all these devices to come to the same platform, and therefore you need standards. Okay. Now, these standards are developed by the standards body. Okay, so there is a world standards body which is the 3GPP, which does this standardization things. Okay. Now, each of these countries in the world, they have a representation in this standards body. So, for example, in India there is a TSDSI, okay, which does this standardization things, which represents India in that standardization body. Okay. So, if India wants to push something into these standards, it will use this mechanism. It will go to the TSDSI, and the TSDSI will put that India requirement onto that standard. And then it has to be agreed by all the countries. Okay, so it's a big platform. All the world countries have to come together, and there must be a consent on what kind of technology you want to have for, let's say, 6G or beyond. Okay. So this is how the standardization process is done. So each of these countries, different countries, then different industries, for example, your Samsung, Qualcomm, and so on, they will come together in this forum, in the 3GPP, and they will decide on these standards. Okay. Now, standards are partially technical and partially political also. Okay, because if you see why the 3G, as I talked about 3G, right? Why the 3G didn't pick up? The reason is, one of the reasons is that 3G worked on CDMA, which was licensed by Qualcomm. So for every chip that you buy for 3G communication, you pay to Qualcomm. Okay. So everything is governed by economics. So this time we have seen in 5G, and now we are seeing in 6G, there is a huge push from the government of India to push our standards, our requirements into these standards. And there is a huge push to build patents across this 6G technology so that the India becomes the world leader. So that whatever chipsets, whatever mobile phones we are purchasing for 6G, the money goes to the Indian companies or the Indian inventors, not goes to the foreign inventors. Okay, so it's a huge market, huge ecosystem that is being built up across these standards. So I would urge all of you to take up research in this 6G dimension so that you can contribute to the growth of the nation also. Okay, because why should we be paying to the other nations? Okay. So how now we are on the start of this 6G, so we need to first define what are the requirements of 6G. What do you all want from the 6G systems? Okay. So this IMT, which is part of ITU, as I talked about, the National Telecommunications Union, it actually decides what requirements the 6G should meet. Okay. So it will give certain features, certain directions. Okay. So these are the directions that have been given by the IMT. So I'm going to list it out and then try to explain some of them. So first one is the inclusivity. Okay. So bridging the digital divide. So that is meaningful connectivity to everyone. So what does this mean? Is that suppose you come up with a technology which is quite costly, very expensive. Expensive in the terms that building devices around it is tough, so it becomes costly. Having core network or backhaul networks is costly. So it will be very expensive. So if it is expensive, then common people will not afford. Only the middle or upper middle will afford. The lower classes will not afford. So then there will be not inclusion of the technology to all the people in general. So what we want is inclusivity. We want to bridge the digital divide. So now also if you go to the villages, you will see the rickshawalas, they are using those small phones working on 2G. Still. Okay, so this is a digital divide. They cannot use the broadband, they cannot use the high-speed internet that we are using. Okay. Then we want ubiquitous connectivity. The second point is ubiquitous connectivity. What does this mean? Now, I come from Ropar. Ropar is a small, it's a district in Punjab. But my college is around 7 kilometers from the city and the connectivity is really poor there. So sometimes there will be a broadband connectivity on my mobile phone, sometimes it is not. And I hope the similar thing will be, you would be also experiencing here also. So if you go to the villages, you won't get proper 4G connectivity for proper internet connectivity. So what do you want is that your 6G system should be capable enough to provide connectivity to each and every person on this earth. Whether he is in a remote farmland, okay, remote rural area, or he is traveling in an ocean on a ship. You should be able to provide connectivity. So that is this ubiquitous connectivity. You want connectivity to each and every person on this planet. Second, the third thing is sustainability. Now you know that these communication systems, when you deploy the base stations, when you deploy the core networks, they take energy. Okay, they work on powers. You have to power them using maybe diesel engines, diesel generators, or through electricity. Okay, so you want your communication systems to be energy efficient. Okay, so that is the third requirement. The fourth one is the innovation. Innovation in the terms of improved user experience. So we want that certain algorithms should come up so that our user experience could be improved. For example, sometimes you are going through an area where the connectivity is low, and whenever you are connecting to the network, the connectivity breaks, there are call drops and so on. So these things should not be there. Then you want enhanced security and privacy. With the Internet of Things, the fans, your light bulbs, your all the electrical appliances in your home, they could be connected to the Internet. So there comes the privacy concerns. It should not be that the hacker comes and hacks your home automation system and then creates trouble for you. So you want enhanced security and privacy. Then you want resilience. So if there is a disruption in the network, it can quickly adapt. Then standardization of and interoperable interfaces. So when you are designing these devices, you want to. So how these devices are designed is basically, you see there is a modem, then there is a processing unit, then there is your screen, the UI, the user interface. So this is how your mobile systems are built. Okay. Now, if you go to the market, if you see how these systems are manufactured, you will buy some chips from someone. Let's say Qualcomm sells you the modem. Then the screen is, let's say, sold by some other company. Then your storage device is sold by some other company. So these things should be interoperable. You should be able to combine all these things together on a chip and build a device. So therefore, this standardization and interoperable interfaces is very important. Now the Indian market is such that if you see the Indian market, there are a lot of small companies building small components for the mobile phones. Now we want interoperability so that these small companies can play a part in the 6G ecosystem. They can give small things, and the other persons, let's say the third party assemblers, they can assemble it and make a smartphone out of it. Then we have interoperability. So we want cooperation between the different networks and different parts of the network. Okay. And then there is interworking. So if you want to have ubiquitous connectivity, that means you want to be connected in the ocean, in the mountain, in the desert, anywhere you want to have connectivity. You can't just do it with the terrestrial base stations. Terrestrial base stations means the base stations that are on the ground. Okay, you have to go to the SATCOM. So you must be hearing about these LEO satellites that are going to provide you the internet. So yeah, Starlink. So there we want interworking. We want interworking. That means if you have a mobile phone which is on 6G, it should be able to connect to the terrestrial base station as well as to the satellite. So we want interworking between all the networks. So it could have SATCOM, it could have IMTs, your cellular, and other access schemes. So even you could have your Wi-Fi also, which could be a part of this ecosystem. So you have just one mobile phone working on 6G and it is connecting to many different networks. It is connected to Wi-Fi, satellite, cellular, and so on. So there is no breakage in the connectivity. There is no delay in the connectivity. So based on these certain requirements, the IIT has came up with certain applications and services that could be enabled by 6G. Okay. So first thing is the ubiquitous intelligence. So what we are going to see is the application of artificial intelligence and machine learning throughout the communication systems. Starting from the physical layer to the application layer, you are going to see the application of machine learning and AI. And it has a lot of use, lot of scope. For example, in smart cities or autonomous network management. So nowadays, if you see if there is some fault in your network, the network engineer will go and then figure out where is the problem and then rectify it. If you have these AI systems, they can figure out the fault themselves and rectify. Okay. Then we have ubiquitous computing. So we want the data processing. Now the data processing is done either on the servers, data centers, or on the clouds. We want to bring that to the edge now. Edge means on your mobile phones or just beyond the mobile phones. Okay. So we want real-time supports, real-time response response in our applications. Then we want immersive multimedia and multisensory interactions. So we want human-machine interactions, digital twins, virtual worlds. So how many of you know that we are building systems for surgery, remote surgery? Have you heard about, right? So what people are doing now is that you don't have to go to the doctor now. So suppose you want to go and undergo surgery, you do not have to travel to some hospital. Okay, you can get it done here. How? You will have the robotic, the robotic operation theater, and the doctor will be sitting remotely at some place and will perform the surgery. Now, what are the requirements in such kind of applications is that the delay has to be very less. Delay has to be very less means, suppose if the doctor has cut somewhere, it should not happen that after 1 second that cut is there. Or if he is stitching somewhere, it should be done immediately, right? So these things have to be there. Okay, to support such applications, you need very low latency. Similarly, if you see industrial automation, what we are moving towards is now a people-free, labor-free industries. So industry will be completely automated, and it will be just controlled by a single computer sitting up with a person sitting somewhere else. Okay. So again, here also you require very high precision communication systems. Okay, very low latency and very reliable communication. Then we have smart industry applications, as I talked about. So you need real-time intelligence and intelligent device connectivity. Then digital health I talked about. Then ubiquitous connectivity. We want to connect the underserved areas, bridge the digital divide. Then we have integrated sensing and communication. So this is one of the major aspects of 6G, integrated sensing and communication. Now you know that the present communication systems, they are just the transmission and reception of RF signals are just used for communication. Okay, so you have 4G, 5G, you just transmit RF signals, receive RF signals just for communication. Now apart from that, if I want to also understand what is the surrounding around me, you can use the same RF signals just like you do it in a radar system. So in a radar system, you transmit RF signals, collect back the echoes, and then analyze it to understand what is the scenario, where are the objects, and so on. So then similar way, we are going to use the same RF signal for both the communication as well as sensing. So this is the integrated sensing and communication. Okay, and this has huge scope in UAV networks. So you know now the future is of UAVs. We have so much of traffic in the cities that traveling on roads is tough now. So what we are going to see is the UAVs, the drones will land on your house rooftop, and then you take that drone and then fly to anywhere else. Okay. So this will be like our mini helicopters, right? Everyone's personal helicopters. Okay. The challenge here is that how do you design the routes for the drones? How do you establish proper connectivity with the different drones? And so on. So a lot of application areas are there, which could be done with these UAVs, with these drones. Now in these drone systems, you need to have both the sensing as well as the communication facility. Sensing means that you want to know when a drone is flying, who all are there nearby me. Which all UAVs are there nearby me, so that I may route my drone in such a fashion that it does not collide. Now in conventional aircraft systems, you take a flight, okay? In conventional aircraft systems, how these aircrafts route themselves is using the ATC, the air traffic controller. So the pilot will contact the ATC, ATC will tell, okay, this direction you move and so on, okay? Now when you go to the UAV networks, UAV systems, where each one of you have an individual UAV, then it becomes very difficult to connect to the ATC and ATC giving commands, okay, you go here and there and so on. Everything has to be autonomous there. So there you would require integrated sensing and communication, you would require very intelligent routing systems so that they can route your UAVs in the air and get you to the destination. Okay, so we submitted a proposal there was a joint call for proposal by the National Science Foundation US and the DST. So we submitted that there. So we are actively working on this integrated sensing and communication. And then sustainability, as I talked about, we need energy efficiency. So we want to have socio-economic sustainability and circular economy. So we want our systems to be recyclable, systems to be reused and so on. Okay. So wherever these the ITU or IMT comes up with certain requirements, it also shares a nice pictorial diagram for us to get a nice visual feel of it. So this is a nice wheel diagram that the IMT came up with. So in the middle you see a triangle here. Okay. So the triangle was a part of IMT 2020, that is 5G. So IMT 2020 is 5G, IMT 2030 is 6G. So the 5G was focusing on three aspects, which was enhanced mobile broadband, ultra reliable low latency communication, and the massive machine type communication. So these were the three things that the 5G was focusing on. Now in 6G we are expanding into 6 things. The first one is the immersive communication, the second one is AI and communication, third one is hyper reliable and low latency communication, then ubiquitous connectivity, massive communication, and integrated sensing and communication. So you can see the green dots, they are actually expansions of the 3 pillars in 5G, and the blue dots are the new added ones. So AI, ubiquitous connectivity, and integrated sensing and communication. These are the new additions to 6G. Okay. Yeah, so I should highlight this part. So as I talked about, when these standardizations are done, all these countries take part together. Okay, these countries come up together and they decide on what kind of requirements the next generation communication system should fulfill. Okay. Now this ubiquitous connectivity, this has been proposed by India and was accepted in IIT 2030. So this is a major contribution from Indian side that India pitched for ubiquitous connectivity and it got accepted. Okay. Okay, the second diagram is the capabilities of IIT 2030. What are the capabilities that you are going to see? So this is the palette diagram. So you see the green ones are basically the enhanced capabilities from 5G. So in 5G you had certain latencies, certain reliabilities, certain mobility and so on. You want to enhance that further. So these greens are those. So that is peak data rate, user experience data rate, spectrum efficiency, area traffic capacity, action density, mobility, latency, reliability, security and resilience. So these all are part of 5G, but you want to have a more data rate, more latency and so on. So enhanced version of those. And the blue ones are the new capabilities that IIT 2030 or 6G is going to come up with. That is coverage, so you want ubiquitous coverage, sensing related capabilities, applicable AI related capabilities, sustainability, interoperability, positioning. Okay. And in this actually many of things was discussed was pitched by India, and one of the major things that India pitched here is the interoperability. And the reason is that, as I talked about, the Indian market is such that there are a lot of small manufacturers that build small components for the mobile phones or for the cellular networks. So we want all of them should take part in the ecosystem. It should not happen that only a big player can take part in the market and small players are left out. Okay. So interoperability, they want that all the systems should be interoperable with each other. So let me spend a few minutes to define the Indian telecom revolution. So in 1998, we had 2 crores landline connections. And if you see now, we have more than 100 crores mobile telephone subscribers. So you see the gain that we are seeing. And everyone across the globe is eyeing on the Indian market. So Indian market has a huge potential. So even you see now also, there are a lot of people who are working still on 2G, not migrated to 4G. So there is a huge potential in the Indian markets for the mobile phones manufacturers, for the service providers, and for the applications. So see, every day new applications are coming up using the mobile phones and the networks. Okay. Annual smartphone purchase is greater than 16 crores every year. And you see now if you see 2G or 3G, mobile phone was just used for communication. So if you want to talk to your friend or to your relative, use the mobile phone. But now the need has changed. You need mobile phones for even livelihood also. So if you see a courier guy coming to deliver a courier, he'll ask for an OTP. He has a smartphone. Okay. So all these things, even you see the food delivery boy, he is also carrying a smartphone. So now the profession also has shifted to the smartphones. Okay. Even the banking, everything you see has now shifted to the smartphones. So a smartphone is not just now a communication device, it has also become a livelihood for everyone. So this is the Bharat 6G vision. So in March 2023, this year, March, the DOT, Department of Telecom, came up with this Bharat 6G. So this is a vision document of what the India is going to bring about in the 6G arena. Okay. So this is a diagram that I have taken from the Bharat 6G document. And it talks about basically the ubiquitous connectivity. So what are the connective things you are going to see? And some of the use cases I have highlighted here, which is the remote controlled factories, as I talked about, constantly communicating self-driving cars. So if you see what is going on is that so of course our private cars, that is the personal cars that we drive, so that is one thing. But there is a huge innovation required in logistic transportations. For example, these truck drivers. So truck drivers drive those trucks for thousands of kilometers, and sometimes overnight, sometimes without taking any rest and so on. So there is a huge burden, a huge strain on these truck drivers. So there is a huge need for automating these truck driving, and so therefore there is a need for self-driving cars. So in future we are going to see these self-driving cars where you don't need any drivers. It will just sense the area and then drive accordingly. Then smart wearables. So everyone is using smart watches, which can measure your temperature, heartbeat, respiration, and so on. We want even more better sensing of our human body, our environment, and so on. Hyperconnectivity, counter rural exodus and metro-driven urbanization. So everyone is moving towards city. Why? Because of livelihood. So you see the cities are crowded and the villages are getting vacant. Okay. So we want to stop this because there is an ecosystem that has to be maintained. The city cannot handle so much of pressure. There are not so much of resources which it can provide to all the users, and therefore you see a lot of traffic, pollution, not proper drinking water facility, and so on. A lot of things are there. So we want to have hyper connectivity, means that the connectivity is there in the village as well, so that a person in the village can also work and earn his livelihood. Okay, so just like we saw a couple of years back when there was COVID, so everything came on the online platform, and I had many of my students who were living in the remote area, and they said, okay sir, I cannot join the class because internet connectivity is poor. So what I have to do? I have to go to the city where the connectivity is proper, and then I can join the classes. So we want to stop that part also. So we want to have hyper connectivity so that everyone is equally connected. So this is the vision for 6G device universe. So 6G is not just the communication, but it is a complete ecosystem. So you require the 6G communication platform, the protocols, networking, stacks, and so on. Then you need chips, modems, then you need the phones, you need the equipments, then you need the systems. Okay. So there's a complete ecosystem that is built around this 6G systems. So 6G is not just a small thing. Okay, just 5 will replace by 6 and it is done. No. It is a complete ecosystem where a lot of people, a lot of companies, a lot of organizations are involved. This is a brief roll-on time for 6G. We are here in the research and development phase. So how it actually works is that we first define the requirements. So till 2024 there is initial requirement studies and so on. And then to meet those requirements, you have to do research and come up with technology. So that is called as the R&D. Okay. So to meet those requirements, you do research, you build prototypes, you test your systems out. Okay. So you say, okay, with this technology, I can meet this requirement of 6G. Once that is done, then you come to the standardization. So I will come up with some technology, you will come up with some technology, and so on. Then we will sit together, discuss, and then come up with a common thing. Okay, this should be the technology that we should go for. Okay, and then once that is done, then you see the commercial deployment. So in commercial deployment, you will then see the devices built up across this standard, and then people using it. Alright, so this was my first part of my talk, where I talked about the 6G systems. Okay. So you now have some flavor of what we are going to see in 6G and how actually it proceeds, how the technology proceeds. Now I'm going to discuss about what we are doing at IIT Ropar to meet some of the requirements of 6G. So we are working in multiple areas. We are working on AI and communication. We are working on intelligent integrated sensing and communication, and we are working on many other technologies also. For example, we are working on RSMA. We are working on underwater communications. For the present talk, I am going to focus on the AI and communication. So we are going to see how the machine learning and artificial intelligence can be applied to communication systems. Now there are many areas where you can apply ML AI in the communication systems. What I am going to do is I am going to touch as the very basic level, which is the physical level. Okay, I hope you all are familiar with the networking stack, the open system interconnections. So you have the physical layer, the MAC layer, network layer, transport, and then so on. So I am going to discuss from the physical layer perspective, and I am going to talk about a very basic thing. Okay. So, so just a simple basic concept. So, how do we transmit our message signal? We do modulation, right? How many of you are familiar with modulation, especially the duplex? Everyone of you. So you have some message signal to basically modulate. You take your high frequency carrier, you might modulate some properties of this high frequency carrier with respect to the message and then transmit. Okay. And why do you do? I'm not going to touch that part. So then you have two types of modulation, analog and digital. So analog, you have AM, FM, PM. Analog is now almost obsolete now. We have moved to the digital modulation schemes. So we use mostly the PSKs. Okay, so how many of you are familiar with the binary phase shift key? Students? Yes? Okay. Okay, then that's good. So I'm not going to explain much, but in short, so what is BPSK is that you have bit 0, you have the same carrier. For bit 1, you phase shift the carrier. Okay. Now, what I'm going to do is that I'm going to talk about first the conventional way of receiving the BPSK signal, and then if I employ machine learning to it, then how the receiver structure changes and what performance improvements it brings. Okay. So this is first the transmitter part. So if you have a BPSK signal and you want to transmit it, how you are going to do is that you will take your binary message signal. First do a level conversion, you do a line coding, then you up convert it, pass it through a pulse shaping filter. How many of you understand what is a pulse shaping filter? How many of you understand what is ISI? Intersymbol interference. Okay. Yes. So to counteract that intersymbol interference, you do some pulse shaping. Okay. And then once you did the pulse shaping, then you multiply it with your high frequency carrier, and then you transmit it. Okay. Okay. And then what you do at the receiver part is you take your received signal, multiply it with the local oscillator, pass it through a low pass filter, then you do an integration and then you do a threshold. Okay. Now, so here you see the main problem here is that if you see this, the carrier that you used at the transmitter, that is cos 2 pi FCT. So FC is the carrier frequency. What you do at the receiver is you multiply your received signal with the same carrier. Okay. Now what happens is this carrier at the receiver, this is again locally generated. How you generate a carrier? You use crystal oscillators. Okay. Now no two crystal oscillators are going to give you exactly the same frequency. Okay. There will be some here and there because of temperature variations, mechanical devices and so on. Okay. So there will be a little bit of variation. So what will happen is that there will be a small phase shift, frequency shift. When there is a frequency shift here, what happens is it propagates to the other parts of the receiver. Okay. Now there are systems which are built which can synchronize your receiver frequency with what you transmit. So this is called as the frequency synchronization. Okay. Okay. So some of the challenges that you face in a conventional receiver is, first thing is that your signal is corrupted by noise. So you have a lot of noise in your signal, so you are not able to decode it. Then you have a path loss. Path loss means as the signal propagates through the medium, it will attenuate. Then you have fading. Then you have a synchronization issue. This is a big issue. Okay. Now what happens is when you are traveling at high speeds, suppose you are in a car or on a train, Vande Bharat let's say, which moves at 160, but now we think we will have semi-high speed trains which will be even faster. So when you are moving at a fast speed, you know that there is a Doppler. Okay, so there will be a Doppler shift in your signal. Okay, so because of that Doppler shift, what will happen? Your frequency will keep on changing, fluctuating. And because of the fast changing the channel, and if you're using large bandwidth, you're also going to see frequency selective fade. Okay. So because of all those things, you will have certain synchronization issues at the receiver. So receiver has to synchronize the frequency phase again and again. And then there are hardware imperfections. Hardware imperfections means that the crystal oscillator or the different devices that you are using on your mobile phones or on your transmitter and receiver, they have to be very precise and resilient to different fluctuations to temperature, pressure, humidity and so on. So if you change the temperature, your oscillator's frequency will change. Okay, and so on. So because of those, there are certain fluctuations in your transmitted signal. Now what we want to do is that we want to use machine learning to resolve these issues and decode our signal properly. Okay. So a little bit about machine learning is that machine learning is basically, it is a system which could basically learn certain functions. Okay, so you give certain training data so that it learns certain function about the channel, about the environment, about the device. And then once it learns the function, then you apply the inputs to it and it will give you the corresponding output. Okay. And you know there are a lot of algorithms for machine learning also, neural networks and supervised, unsupervised, reinforcement learning, random forest and so on. And the application areas are also huge. So this is how you apply the machine learning. First you train your algorithm and then you test it out. That means you have deployed in the field. Applications are huge in healthcare, automation, image processing, stock marketing, language translation and so on. And in wireless communications there are also a lot of applications: signal detection, modulation, detection, channel estimation, beamforming, channel coding, waveform generation, spectrum availability, prediction, RF fingerprinting, resource allocation, path planning, UAV trajectory prediction, waveform generation. So a lot of applications are there of machine learning and communication. So before moving on, how do we apply machine learning to communication? We have to first understand what kind of signals we get from the channel. Okay. So when a signal is transmitted, it is received, we get something, right? What that something is, first we have to understand that. So just a word of caution here, or an advice. So we have been working on this, machine learning, with these machine learning algorithms for almost 4 or 5 years now. What we have understood is that there are a lot of good machine learning algorithms, but unless and until you understand where you want to apply it, you are not going to get any result. Unless and until you understand where to apply it exactly, you are not going to get any result. It is not just that you apply it anywhere and you get it. No, it doesn't work like that. So first thing is, you first understand what the signal is all about, what you are getting. Okay. So what we do in our lab is that I'll show you in the later slides. I'll talk about the hardware prototypes that we have developed, how we do the experiments. So we use something called as the software-defined radios. Now what are these software-defined radios? Are basically small kits. I think you would have used microprocessor kits to program them in your labs, right? In a similar kind of thing, there are kits wherein you can program your wireless communication systems. So you program it using MATLAB or any other software, Python and so on. It can transmit in the air, and then you have another kit which would receive, and then you can process it. Okay. Now when we are working on all these kits, we first need to understand how or what kind of signals you get in these kits. Okay. Now all the processing now is done in digital domain. Previously, when there was analog systems, when you had AM, FM, right, they were all done in the analog domain. Now everything has shifted to the digital domain. Okay. Now what happens when you go to the digital domain is that you need to first understand what signal you are getting in the digital domain, and then you have to correct for all these imperfections. For example, you have to do frequency synchronization, phase synchronization, timing offsets, and so on. Everything you have to do in the digital domain, not in the analog domain. Okay. So okay, I don't have that slide, but I will just speak it briefly. How do we get the signal? So first thing is you have your RF antenna which collects the signal. Now this is first filtered, so filtered for the desired frequency band that you want, and then it is amplified. Then it is multiplied with a local oscillator. Okay, so suppose if you have cos 2 pi FCT, so let's take this one. So you have the received signal, which is H is the channel gain, channel fading coefficient, Xt is your transmitted signal, plus Nt is your noise. Okay. So when you take this signal, you multiply it with the local oscillator, which is cos 2 pi Fc plus delta Ft plus theta. So here I am saying that your local oscillator has some frequency offset, which is delta F, and some phase offset, which is theta. Okay. Now, once you multiply this, what you are going to get is, suppose you transmitted A cos 2 pi FCT. So you will have A cos square 2 pi FCT plus some component of cos 2 pi delta Ft plus phi and so on. So you will have some high frequency components, some low frequency components. High frequency you will discard. Low frequencies is what you want. Okay. So that is a low pass filter that you apply. Okay. After that, what you do is you do a sampling, because everything has to be done in the digital domain. So first thing is you do the sampling, bring it to the digital domain, and then you do all the processing in the DSP, in a digital signal processing. So once you are doing the sampling, so what you do is that you take your cos, you multiply first with cos, the other time you multiply it with the sine. When you sample the cos component, you get the in phase I. When you sample the sine component, you get the quadrature or the cube. Okay. How many of you could understand this part? How many of you could understand this part? This is important part. Okay. So let me explain again. See, when you are transmitting any signal, let's say you want to use carrier frequency Fc. Now you know cos and sine are orthogonal to each other. So what you can do is, you can modulate sine as well as cos. Okay, so you modulate with cos 2 pi Fct, take one stream, another stream you multiply with sine 2 pi Fct. They are on the same frequency, but these are orthogonal to each other, that means they won't interfere. So when you are demodulating also, what you do is, you make two branches out of it. First one is you multiply with the cos, you get the cos components, you multiply with the sine, you get the sine component. So therefore you get I and Q. I and Q means you get a complex samples. This is I plus JQ, you get complex samples of your received signal. Now once you get these samples, now you push it into your DSP and do all the processing. So there is a lot of complex processing that is going to go into your DSP. It is not very simple. So for all the faculties, those who are here, so what we did is last year we actually conducted a MTech laboratory, communication lab, and in that actually we introduced to these MTech students these hardware kits. So we got a few hardware kits, around 10 of those, and we made them understand how the reception is done in actuality. on hardware. So they did the programming on these devices, and they could see for themselves, once you get these samples, how you do the processing. Okay. So how you do the processing is, first you apply actually the automatic gain control. So you have to control the gain of your signal. Then you apply the frequency synchronization. So you see you have to correct this delta F. Then you apply phase synchronization. That means you have to correct this phi. Then you have to understand the timing synchronization. Timing means, because everything is digital, so your bit period, you understand the bit period. So your bit 0 will be for some time, bit 1 will be for some time, and so on. So there is a bit period. So you have to synchronize the bit periods also. Then you have to synchronize the sampling times. Because your system has sampled, it does not know where your bit starts, where your bit ends. It just samples it. So sampling could be either in the middle of the bit period, or it could be at either of the corners. So you need to correct those errors also, sampling errors. So how you do is, you do an interpolation. Once you get those samples, then you apply your threshold detector. Then you say, okay, for bit 0 I have to see whether positive voltage is there or not. For bit 1 negative voltage is there or not. And then I decide bit 0 or bit 1 and then push it further. Okay. So this is a complete process that goes on in going from the sampled signal to the bit demodulation. Okay. So this is what actually it looks like. Here's the received IQ data, these are the samples. So we collected these data and then I plotted the magnitude over here. So just to show you that this is how your signal is going to look like. And you are going to make nothing out of it. Okay. So this was a brief overview of what you get actually. Now applying machine learning to it, how we applied it is like this. We took the received signal, passed it through the local oscillator, and then of course we passed it through a band pass filter. Rather than a low pass filter, we used a band pass filter and applied the ADC. So the sampling is done here. Okay. Once you do the sampling, rest of the component, rest of the thing is now going to be pushed into the DSP. The digital signal processor, or you have any processor, it will now process your samples. Now we apply the DNN. DNN is the deep neural network. So you know the machine learning, one of the famous algorithms in machine learning is the neural network. And if you increase the layer, make it more deep, it is deep neural network. Okay. So we applied the deep neural network and then we figured out what's the binary output. Now, one important thing that we did here, which is different from the conventional thing, is that, so what happens in the conventional case is when you are trying to correct for the sampling times, or if you want to understand where the symbol is starting, where the symbol is ending, that is the symbol timing you want to understand, you need to sample your signal at a higher rate than the Nyquist. Okay, so I don't have a board here, but if you draw a square wave, and if you want to understand where the symbol starts and ends, acha. How to make it work? Okay.
PPT कहीं पे
So presentation भी लिखना है या फिर इसको? नहीं. So this is your signal that is coming, right? This is a low pass signal. So what you do is basically you have to sample it. Ideally you would want to sample it at the middle of the bit. Okay, so you want to sample it here. But what you do is, and of course you want one sample per bit period. But what do you do in actuality is you sample multiple times in a bit period. So that means you take 2 or more. So So let me draw it like this. So you take two of them. Okay. Why do you take this? Because you want to understand where the bit is starting, where the bit is ending. One sample cannot give you that information. So you need multiple samples. That is first thing. Second thing is, once you have done the sampling, you cannot change the samples. Once you have sampled the signal, you cannot change it. You got the samples, that's it. Not a DSP has to do everything. Now in this orange case, if you see, ideally I should sample it here. But my orange, if you see, it is shifted. What it will give rise to? Suppose if there is a ISI, what will happen? This will merge into this. So your signal will be something like this. So if you sample at the edges, you will get noise or interference from the previous symbol. So you need to correct for the simple sampling times. So what you want is your orange should come here. So here you should sample. So what you do is, you go to the DSP, apply the multi-rate signal processing, and you interpolate. You first take these samples, go to a higher rate. Higher rate means you will get samples in between these, and then you interpolate from these two what should be the value here, and then you use these samples. Okay, so it's a complex process. I'm just telling you in very briefly. So this is how you do in your communication systems. You first sample it, correct for the symbol timing, and then the sampling times. Okay. Is okay? Okay. Yeah, so I was talking about that thing. The one thing that we introduced is that we sampled a higher rate than is normally done. Okay. So let's say we sampled, we got 5 samples per bit. Okay. So this is what we defined actually K here. So filtered signal is sampled using analog to digital converter, giving K samples per bit period. So we have defined K, but K could be ranging from 5 to 20. Anyway. Now what we did is that we took our hardware, which is our SDR, software defined radio, and we coded it with our machine learning based demodulator. So how we did it? Took the received signal, we applied a raised cosine filter, AGC, symbol carrier synchronizer, symbol preamble detector, and then we applied the DNN, which is we call it as deep D1, which is the deep neural network, which is able to demodulate our received signal. So this was the architecture of the DNN. So we took 5 layers in the DNN, and then 7 neurons, and then all the things are there. And what we did is that you know that all these machine learning algorithms, you need to train them first. So in training was the trickiest part. So what we did is that we took half the synthetic data. Synthetic means generated using MATLAB, and half data we took from the environment, the measured data. We combined these two together, made a pool of a big data, and then trained our model. So once you train our model, so this is how it is going to look like. So over a bit period, you get multiple samples, which is going to fluctuate like this. You take these set of values. For these set of values, you get one output, which is bit 0 or bit 1. Okay, so K is your input layer and 1 is your output layer. Okay. And then you know that the wireless channel keeps on fluctuating. So you need to retune your machine learning algorithm so that it adapts to the changing environment. And this is what we did using using transfer learning. So you know that in packet transmissions, you transmit something called as pilots. Now pilots are used to estimate the channel. So you use the same pilot to retune the DNN to adapt to the environment. Okay, so DNN will learn how the signal is mapping, and then it will adapt to the environment, and then it will be optimal for that environment. So just like everyone does, what we did is we started first with the simulation exercise to see whether the improvements are there or not, and then we moved to the hardware part and showed in actuality how the improvements are. Okay. So this one is the bit error rate versus SNR in AW chain channel. So everyone of you understands the AW chain channel, so it has no fading. Okay. So the green one, if you see, that's a conventional demodulator. So bit error rate, the lower the better. So you see the conventional is quite high, and if you see our deep demod, that is the deep learning based demodulator. So for different values of k is the number of samples per bit. So we have taken 10 and 50, and TL is the transfer learning based. So if you see, the performance gap is huge. So for getting, let's say, 10 to the power minus 3, I would get it at minus 15 dB, as compared to in the conventional case you will get it at 8 dB. Okay, so see the gains here. Okay, and similarly we observe it for the fading channel also. For the fading channel, and when there is a phase and frequency offset between the transmitter and receiver, then the conventional, the PER is quite high. For 10 power minus 1, you need a bit, you need an SNR of let's say minus 5 dB. As compared to in our case, it is minus 15 dB. So more than 10 dB of gain you can see in the machine learning based demodulator. Okay. And then you would be wondering how the system will perform if we increase the number of samples per bit. So we actually started with 10 and went up to 10.3, so 1000 samples per bit. So if you keep on increasing the number of samples, you are going to see huge improvements in the PER. Now the side effect is that if you collect more number of samples, then your processing also increases. So you have to sample those many, you have to process those many samples for every bit. So this is our experimental setup. So we first started with the lab. So you see these green boxes here. So this is your USRPs, as I talked about the software defined radios. Then you have the antennas, and then you program it using your laptops and computers. Okay. So one experiment we did it in lab, then we did it in the corridor, and then we did it in outer space also. I'll show you that also. So this is the result that we got from our experiments. So indoor and corridor and outdoor also it is there. So we took k is equal to 5 only. So 5 samples per bit. So here is the conventional, the green one. Again, the green one is the conventional one, and this is our deep demod, which is the deep learning base. So let's say for 10 power minus 2, I would achieve at 2 dB SNR, as compared to this one will achieve at 14 dB. So again, you see 12 dB of improvement. Okay. So these are experimental results. Okay. Okay, so this is first part of my research talk. So if you have any questions, I can take it up now, or otherwise we will move forward. All right. So till now we talked about CISO system. CISO means
Single input.
single input, single output. That means single transmit antenna, single receive antenna. Now you see our communication systems are now becoming minor. Everything is minor. So you have multiple transmit antennas and multiple receive antennas. So we are going to take one step forward, and now I am going to talk about meso system. MISO means multiple transmit antennas, single receiver. So let's do this. So this is MISO. You have multiple transmit antennas, and there is one receiver, which is a single antenna. Okay. So what is the gain that you get in MISO system? Why do you want to go to MIMO? What is the motivation behind going to MIMO system? Anyone?
Better data transmission.
Better data transmission. Okay. And high throughput. Okay. Anyone else? Energy consumption is less. Okay. Anyone else? Okay. Why you get high throughput? Can anyone tell that? Why do you get high throughput in MIMO systems? Sorry? Connectivity. Faster connectivity. No, give a technical answer.
It's a reliable communication.
Yeah, but why is it reliable? Why it gives a reliable communication? So you know one of the major problem of wireless communication is fading. What is fading? I mean, you see, when I am transmitting a signal from here to there, the signal can go directly. It will reflect from the wall, from the floor, from the ceiling, and so on. So at the receiver, what will happen? All the signals will combine, add up together. So suppose if two components are out of phase and adding, what will happen? Destructive interference. If they are in phase and adding, constructive interference. So what is fading? The fluctuation of the signal. So sometimes constructive, sometimes destructive, so it will fluctuate. The signal amplitude will fluctuate at the receiver. This is fading. Okay. Now if you have one single path from the transmitter to receiver, and suppose at one time it is in deep fade. Deep fade means the signal at the receiver is combining in such a way that it is destructive interference. Then what will happen? You won't get any signal at the receiver. So this is called as deep fade. Okay. Now if you have two antennas and of course the same receiver there, same receiver antenna, the channel from the second antenna to the receiver may not be in deep fade. Okay. So just like what you guys will do is that you will take offer from two companies. Okay. And then you say, okay, if one company goes back, I have another company to rely on, right? Always we make these two options. We have two or multiple options we keep. Okay, so one option goes back, the other option is there too. Same thing here in MIMO also. So if one of the channels is in deep fade, there is a less probability that the second channel will also be in the deep fade. So if you keep on increasing the antennas, there will be more possibility that one or multiple channels will not be in deep fade, will be in a good state, and so you can communicate with them. So therefore your reliability increases, your data rate increases, so this is called as a diversity gain in MIMO systems. Okay. So this is why if you use a MISO or a MIMO, you get those gains. So here I have listed the gains. So receiver gain, then rate, then SNR, all these things increases. Now, how the current demodulation is done for a MISO system, let's understand that part. So what you will do is that your transmitter, what it does is that it transmits through multiple antennas the same signal. Now, when you're transmitting through multiple antennas, you don't transmit the same signal exactly. What you do is you multiply it with some weights across each of these antennas. Now these weights depend on the channel that you are experiencing between these antennas and the receiver. Okay. And the technical term is called as the maximal ratio transmission, MRT. Technically. So if you use MRT, then we say that we will receive the maximum SNR at the receiver. If you do MRT. Okay. MRT means you decide the weights of these transmit antennas in such a fashion that you get maximum SNR at the receiver. So there is an equation to it, so I am not going into that. So you basically do an optimization and figure out what should be those limits. Now what is the challenge here? So suppose if you have more number of antennas, then you need more number of channel and state information, H values, the CSI. So you need to first estimate those CSI, the channel states, and then you use it in your algorithm and then transmit. So that is one challenge. The other challenge is suppose you moved to another location and the channel changed for all those antennas. Then you have to again re-estimate. So there is a mobility issue. And then the dynamic channel means the channel has also changed. So suppose the object was somewhere here, after some time it moved to another place. So again the channel changed, so you have to again re-estimate. So re-estimating these channel state information is critical in a MIMO system. Okay. So though we are pitching for massive MIMO or ultra MIMO systems, this is a huge challenge. Getting the H values. H values is the channel estimation. So, and of course what it actually results in the complexity, latency and power constraints in the receiver. So what we do is that we will use the deep learning, deep neural network to receive this meso channel, meso signal and demodulate the signal without using channel state information. Without using CSI, we are going to demodulate the signal. Okay. So again the same thing we do, we receive the signal, applying, we multiply with the local oscillator, the low pass filter, then unlock the digital converter and then do the DNN, the neural network. Okay, so I am going to show you the simulation results now. So this is the simulation result. So again the green one is the conventional demodulator for one transmitter, one receiver. And then we have LMUT for two transmitter, one receiver. So if you are using meso system, LMUT is the optimal solution. Okay, so that's the LMUT. Then we have the maximum ratio transmission. Channel is estimated, which is two transmitter, one receiver. MRT with channel 1, two transmitter and one receiver. Okay. So these four are here. You can see the bit error rate performance of these conventional systems, and if you use the deep demod, you can see the performance improvements here. So with k is equal to 50, you are going to see these two, and with k is equal to 10, you are going to see these two. Okay. So let's say for 10 power minus 2 BER, I can achieve at minus 17 dB versus if you use that, you have to have 6 dB SNR. Okay, so 20 dB SNR gain. Okay, so this was for the fading channel. I mean, I'm not going to discuss that again. Same thing. Yeah, so this one was the, again, we did the experiments for this also. So this is our transmitter with two antennas. Okay, and the receiver is on the other part, and then we did it in an open area. Okay, here. And these are the experimental results. So four things I have plotted here: the conventional 1x1, 2x1, and the ML based detector 1x1 and 2x1. So if you see the green and red, so these are these two. So again for 10 power minus 4, you can get it at 17 versus 21. And if you use a ML based detector for a meso system 2x1, so this is the purple one and the blue one. Okay. So again for 10 power minus 4, you get it at 8 and this one, right? 8 and 21. Okay. Okay, sorry, this one also. Okay, so again you can see the gains 15 dBs of gain. So this was about the meso system. I'm going to take just one step more, talk about distributed meso, and then I talk about what is the challenge here. Though you are going to see good gains, but what is the challenge, that is also important to understand. So distributed MIMO, what is the distributed MIMO is, now you see when you have a MIMO system or a meso system, your antennas, your transmit antennas are sitting on the same system. So for example, I have a mobile phone and suppose if it has two antennas, it will be connected to a single crystal oscillator. So single crystal oscillator means that it is being fed by the same source. Okay. Now suppose a case when one antenna is on my phone, another antenna is on your phone. What will happen? The two antennas are going to be fed by the two different crystal oscillators. That means these transmissions will be different. Different in terms of they will have a difference in the frequency offset and time offset. Okay. Now what is the advantage? First come to the advantage. So you see this diagram here. Have you seen ants in such a fashion? Taking up a big thing collectively. Okay. Now you see in IoT systems, you want to have your devices to be very low powered. You do not have the luxury to build multiple antennas on the same device. Okay. Because that will make your device bulky, that will consume power and so on. In those cases, what you want to use the concepts of MIMO, but you want your antennas to sit on different devices altogether. So one IoT device is here, second one could be in another room. They should collaborate together and transmit the information to the receiver. So this is what we want. So multiple transmitters come together to transmit an information to send it to a very farther off receiver. Okay. So you get the gains of MIMO, but the challenge here is all these are not synchronized. All these transmitters, that means all these antennas which are sitting on a different processor and crystal oscillator, these are not synchronized with each other. So what do you need to do? You need to synchronize them. So suppose if ant is there and it is holding some object, you want to move it in one direction, so they have to synchronize, right? So I want to move in this direction. But suppose one ant is moving here, the other here, thing will not move. So what you want is all these transmitters should be synchronized. Now, what is the challenge in synchronization? The challenge in synchronization is that you have to synchronize the frequency and phase of all the transmitters. It takes a lot of time. There are algorithms which does that, but it takes a lot of time. You have to send a reference signal, the different transmitters will latch on to that reference signal, change its transmission frequency and phase accordingly, and then transmit. It takes a lot of time. So instead what we said is let them be unsynchronized. Now suppose if they are unsynchronized, what will happen? Some signal is transmitted here, here, here. There will be some complex structure that you are going to see at the receiver. What we are going to do is, we are going to read or understand that complex structure at the receiver and try to understand what the bit was transmitted. Okay. So this is what we did. How do I rub it? Okay, so in ideal so we call it as distributed beamforming or distributed MIMO also. Okay. So of course you get the same gains as that of MIMO. I'm not going to go into that. So suppose I've taken two transmitters transmitting the same signal, of course with this different frequency and phase offset, you get a complex signal here at the receiver. So from this complex signal at the receiver, you have to figure out what the bit was transmitted. So, I mean, I've given another example is you have an orchestra. If everyone is playing in a different way, you won't get anything. But if everyone plays coherently, then you hear a nice melodious sound. So the same thing here. So these are the challenges: carrier synchronization, phase synchronization, timing synchronization, and coordination of the information between the different transmitters. Okay, so again what we did is, again we applied the deep neural network to our receiver and implemented it on the hardware as well. So again, I'm not going to do the same things. So this is the demodulation performance. So here actually I have project phase offset. Okay, phase offset in degrees versus the bit error rate. So if you have two transmitters, suppose they transmit at exactly the same frequency, but there is a phase offset between the two. Okay. Now if there is a phase offset, what will happen at the receiver? These two signals will combine together. So if suppose if they are 180 degrees out of phase, then these two will subtract and you will get 0. Right? So the same thing you see here also. So if you see here, this is 180 degrees and the bit error rate is 0.5. 0.5 means you are not getting anything. As you keep on decreasing the phase offset to 0, you get the perfect synchronization. That means these two signals will add up coherently. And in between, there is a gray area where you are going to see the change in the performance. Now for the conventional case, these are the conventional case results for different SNRs. So gamma is the SNR. So you see the bit error rate is quite high. So let's say at 100 degrees phase offset, you are going to get this bit error rate, which is 10 power minus 2. In our case, for 100 dB it is almost 0. 100 degrees it is almost 0. So this is for the dB. Okay. So the point I am trying to say is that even if you have an imperfect combination of signals at the receiver, the deep neural network can still decode your signal, which the conventional receiver cannot detect. Okay. So this is one of the advantages of using the machine learning in communication systems. You don't need to bother about the imperfections anymore. The machine learning algorithm can itself understand what the imperfect signal you are receiving, and based on that it can make its decision. Okay. So again we did certain experiments. Yeah, we did some experiments again in the corridors, in lab, and so on. Okay, so there's a video also. So, by the way, this is the constellation diagram. Okay. So this is a practical thing going on. So see, if you change the transmitter, the receiver location, you see a different constellation. So from these constellations, you have to first correct it, figure it out what the bit was transmitted. Okay, so these are the experimental results. So this is the conventional and deep demod, and then for the two transmitter case, it is here, the green one and the purple one. Okay. Okay, let me finish it, and I have one video also. I'll show that. So this is the impact of our work. We can use this particular technology in rural communications, because in rural areas what happens is that you need a larger coverage. Larger coverage means that your signal is attenuating considerably at the cell edge user. So with this technology, you can use your communication systems even at lower SNRs. Then you can use it for 6G, beyond 5G, 6G communication systems. You can use it for cell-free message MIMO. You can have secure communications because what we are actually decoding is a pattern, not the exact signal, but the pattern in the signal. Okay. Then we can use it for low power communications for IoT applications and so on. So the application areas are endless in this case. So this is my conclusion. ML-based algorithms can provide substantial improvements. However, there are two challenges. First thing is you need to understand where to apply the algorithm. Okay, it's just not that anywhere you apply it, you get the results. It's not like that. And the challenges are high processing time, large data sets, and of course these could be used in many other places. We are using it for channel coding, we are using it for trajectory designing, we are using it for joint sensing and communications and so on. So a lot of research is going on in this direction. Okay, so this is our lab at IIT Ropar, which is Advanced Research in Communication. And we do a lot of other stuff also. So we work on IoT systems and security, then UAVs and intelligent transportation systems. So we are building a test bed around this intelligent transportation systems using UAVs and regular stuff. And again, certain protocols and architecture designs. Okay, so with this, let me end my talk. And I want to show a quick video of our experiment that we did.
Thank you so much, sir, for such fruitful and insightful session. I would like to invite our coordinator and co-coordinator of FDP program, Arun sir and Rajiv sir, to present the certificate and shawl to serve.